Hi there, welcome to lecture 4 in Fox, and today we're going to be talking about proofs. Okay, but before we start, let me remind you where we were from last time. Last time we talked about how to make precise statements. Basically, we talked about formulating all our statements using sort of propositional logic, augmented with quantifiers. So propositional logic is you have your basic statements, you have not, and or, and the other main tool is the if-then, the implication. And then we augmented that with quantifiers such as for all and there exists, which allow us to make statements about an entire collection of objects. So it's important to be able to formulate precisely what we want to prove. And today we're going to be talking about proofs. Okay. So the main thing we're going to be focusing on is the if-then, the implication. So how do you prove an implication? Proving an or proving an and are relatively simple. To prove an or, you prove that one of the two things is true. To prove an and, you prove that both of the things in the and are true. But to prove an if-then, that's a little bit more complicated. We're going to spend a lot of time on that. Okay? We're going to develop proof patterns for if-then. And related to if-then is this notion of equivalence. And then we'll sort of talk about another very, very deep proof technique. It's the proof technique we used to prove that the square root of 2 is irrational, and that's contradiction. We'll talk about proving things about sets, and we'll conclude with a sort of a template of when you're faced with a situation where you need to decide how to prove something, what kind of proof should you make. Okay, so implication, that's what we're focusing on for the moment. And let me contrast this notion of an implication with something that we are familiar with in everyday life, which is reasoning. So I came to you and I told you, last night it rained. So that's a fact. You know something. It rained last night. And from this fact, you will deduce that the grass is wet. And that's a everyday chain of reasoning that we're very familiar with. You have no problem with this because of all the wealth of experience you have in the real world. So if I tell you this fact that it rained last night, then you deduce that the grass is wet. So that's everyday reasoning. Contrast that with an implication. Okay, so here's an implication. If it rained last night, then the grass is wet. Now, why am I spending such effort in contrasting this? Because I'm going to ask you the question, well, what do we know? Did it rain last night? We don't know. Is the grass wet? We don't know. And so this is sort of, could be viewed as a flaw with the implication in the sense that it doesn't really tell you anything. Okay, so there are no facts that it tells you. So I'm going to call this reasoning in the absence of facts. Okay. It's not telling you anything, but what it is doing is important. It's linking two things together. It's linking the statement, it rained last night, to the statement, the grass is wet. Okay. It's essentially stating the validity of the tool that we used in the previous reasoning example to conclude that the grass is wet. And so that's the value of this link. The value of this link, the value of this reasoning in the absence of fact. So the value of sort of showing that this implication is true is that if sometime later someone comes to you and says, you know what, it rained last night, you can immediately conclude the grass is wet because we have established the truth of this implication. So that's the value of implications. And now let me show you some sort of more concrete applications of implication in the context of computer science and math in general. So, so here's a claim. Okay, it's an implication. So what it does is it links two things together. And we're not in a stage where we can prove such a claim, but supposing we did. So if we can quickly find the largest friend clique in a friendship network. So we talked about friendship cliques, groups of people who all mutually know each other. So you have a social network like Facebook with 3 billion people. Okay, what's the largest friendship clique? So what's the largest group of people who all mutually know each other? If we can find that quickly, well, here's another problem that we sometimes like to solve. So you have a bunch of radio stations, so many radio stations in the US, they're distributed all over the place. Well, how do we assign non-conflicting frequencies to these radio stations so that nobody hears garbled music? And well, the challenge here is that, well, certainly I could assign a different frequency to each radio station, but I want to assign frequencies as few frequencies as possible, because I want to use a limited amount of bandwidth. So these two problems look completely unrelated. But imagine if I went and proved the implication that if I can find the largest French fleet, then I can find non-conflicting frequencies for radio stations efficiently. So if I can do one, I can do the other. Now, can I find large friendship fleets? No. Well, we don't know. We haven't established that. Can I find non-conflicting radio frequencies for radio stations? No, we don't know that. It's just like if it rained last night and the grass is wet. Very similar. Okay? We don't know anything. We've just established a link. This is a very powerful link. So it means that, for all those of you who want to establish to assign radio frequencies efficiently, you don't need to solve that problem. If someone else has been able to find large friendship fleets in graphs, you can just take what they did and use it to solve your problem. That's the value of this link, the value of this reasoning in the absence of facts. Here's another example that's familiar to you from high school. Okay. So, in high school you learned this quadratic formula, this beautiful thing. Well, let me formulate it in the form of an implication. Okay. So, at the moment we don't know anything, and what we're saying is that, if, okay, now I'm going to link two statements together. That's what an implication is. If ax squared plus bx plus c is equal to 0, okay, and a is not equal to 0, okay, so, if you are in a situation where this is true, okay, then you can conclude that x equals, minus b plus or minus the square root of b squared minus 4ac over 2a, okay, this famous quadratic formula. So what that says is that, it doesn't really say anything. It links these two. It says that if sometime in the future someone comes to you and says, I have an x and it satisfies this equation in a non-trivial way, that is with a not equal to 0. It satisfies this quadratic equation. Oh, then you can come and say, but Malik proved this implication, this link that says that whenever this is true, then we can conclude that x is either this number plus or is minus b plus or minus the square root of b squared minus 4ac over 2a. Okay, so that's the value of these implications. You use them all the time. It may have not been taught to you formally as an implication. It was taught to you as the quadratic formula, but in reality, it is an implication. And that's why we prove implications, because we'll use them later when someone comes and reveals to you a new fact that establishes that the left side of the implication is true, and you conclude that the right side is true. So there's a huge value in proving implications, even though they may not give you any new facts, any new knowledge. It proves relationships between. Okay. So today, we're mainly going to focus on proving implications. Okay, and then we'll talk about, contradiction as another powerful proof technique. And lastly, we'll talk about proofs about sets. Okay. And as usual, when it comes to math and writing proofs and so on and so forth, we're going to move to the board. Okay, so I'm going to be telling you about some proofs, and starting with proving implications. Proving implications means the truth table for implication is extremely important. So I'm going to write it down. Okay, so P implies Q. P implies Q. That's implication. And if I'm looking at the truth table, we'll list the possible values of P and Q. So we saw this before, so I'll do it very quickly. Okay, so P, Q can be false, 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 true, true, false, true, true. Okay, and the implication is only false in the event that you find a situation where P is true and Q is false. So here it's false, and here it's true, true, true. This is so important, I'm going to box it as a reminder to Malik, don't erase. Box, not erase. Okay, and this row in which the implication is false is also going to be very important, so I'll highlight that row. Okay, so this is the row in which this implication is false. Okay. And so let's talk about proving implications. And I'm going to start with two examples of implications. So the sum of two rational numbers is rational. Okay? Example number 1. And example number 2. every even square came from an even number. Okay. So the first thing I want to note is that these are implications, and it may not look obvious that they're implications. So at the moment they're just claims that have been stated in English. So let's convert them to implication and the mathematical language that we talked about last time. So the sum of two rational numbers is rational. Basically what we're saying is that if you have two rational numbers, so if x is rational, so q is the set of rational numbers, x belongs to q. So if x is rational and y is rational, then x plus y is rational. Okay, so the sum, if x and y are rational, so if x and y are two rational numbers, then their sum is rational. Okay, we can further sort of simplify this or put it in more mathematical notation by observing that we'll call this q, p, we'll call this q, and then this is saying that, x, member of the rationals, and y, member of the rationals, implies x plus y is a member of the rationals. So x and y are rational, implies x plus y is rational. Okay, we'll do the same thing here. What do we say? Every even square. So if you ever happen upon an even square, so if it's a square, so if n squared is even, okay, so every even square came from an even number. What they're saying is if you come upon an even square, it must have come from an even number. So if n squared is even, then it must be the case that n is even. Then n is even. So I've taken an English claim, put it into an if-then form, and now I'm going to make it more mathematical by saying that this is basically the compound proposition or the implication. N squared is even implies n is even. Okay, and in this case, this is p and this is q. We have p implies q. P implies q. And now we're going to address the issue of how do we prove these claims? How do we prove these implications? And okay, let me first step back and sort of address something that might be a little bit scary at the moment. Okay, what is scary at the moment? I'm asking you to prove something, okay, and it's this something that involves x, y, or in this case n, and we actually don't know anything about the variables that are involved. So I'm asked to prove this claim. X is rational and y is rational implies x plus y is rational. Well, what is x? Don't know. What is y? Don't know. Are x and y rational? Don't know. What we're asked to prove is a link between two claims. That's what an implication is, and that's what makes it subtle and hard to prove. Okay, for example, here, what is n? We don't know. Is n squared even? We don't know. All we're saying is that if you ever end up in a situation where you have an n squared that's even, it must be the case that n is even. So there's this link. But I don't know at this moment what is n. I don't even know if it's even. I don't even know if n squared is even or odd. Okay? And we will never know. All we're doing is proving a link. Reasoning in the absence of facts. We have no facts. We're just proving a link. Okay. So how do we prove it? How do we prove such a link when we don't know anything about x and y? And that's where the truth table comes in. It is absolutely fundamental. Okay? So we're asked to prove that an implication is true. Okay? So we look at the truth table and see when is it true. So it's true, true, true. Here's the situation where it's false. So equivalent to proving that it's true, we may show that it is not false. Okay? And because there's only one situation where it is not false, proving that it is true essentially amounts to showing that this situation cannot occur. This row in the truth table cannot occur. To prove P implies Q, show that this row cannot occur. That's a fundamental idea. Okay. Fundamental idea. Okay. So let's see how that can work when we don't really know anything else about x and y or x plus y in this situation. So how do we show that this row cannot occur? Okay. So step one. In this row, it is the case that P is true and Q is false. So, step one. Let's see
what happens if P is true? If P is true. Are we saying P is true? No. We're just saying, let's see what happens if P is true. Imagine I jump into a fictitious world, okay, and in this fictitious world, it so happens that P is true. So I arrange a fictitious world. I'm pretending that P is true. I'm not claiming it's true. I'm just pretending it's true. Okay, what does that mean? What does that mean? Well, if P is true, in this case, P is the claim that X and Y are both rational. It means that X is rational and Y is rational. What does that mean? That means that X equals a ratio, A over B, and Y also equals a ratio, C over D, where A is an integer, B is a natural number, and that's nice because B is in the denominator, it cannot be 0, and that's one of the advantages of the natural numbers starting at 1. So it's 1 and bigger. So B is a natural, and C is an integer, and D is a natural. So that's what it means. If I end up in a world where P is true, that's what it means. Okay? Now, what does that say about Q? Why am I even worried about Q? Because I'm analyzing this row in which, the implication is false, and in this row, we start off with by being in a world where P is true, and then we ask, what does that say about Q? Okay, so let's see, what does it say about Q? Well, Q is a statement, a claim that or proposition that involves X plus Y. So we have to look at X plus Y. So X plus Y. Well, what is X plus Y? It's A over B plus C over D. Is A over B plus C over D, and we all know how to do basic high school algebra. This is A D plus B C over B D. But look, B and D are natural numbers, bigger than 1. So the product is a natural number. Okay, so this is and A, D, and B, C. A, D is A and D are, A is an integer, D is a natural number, so the product is an integer. B times C, again, product is an integer, so the sum of two integers is an integer. So I'm relying on your high school math to sort of inform you that the top guy here is an integer and the bottom guy here is a natural number. Okay? But that is exactly what it means to be a rational. So X plus Y, so X plus Y is a rational. That's what it means. Okay, but so why did we analyze X plus Y? Because Q involves X plus Y. And so what does the fact that X plus Y is rational ultimately say? It ultimately says that Q, the proposition that X plus Y is a rational, Q is a true statement. This says that. This says Q. Okay, now, do we have a choice? No. It must be true. So let me summarize what we have done. We went into this fictitious pretend world in which, we have constructed this world where somehow P is true. Okay, but that's the only sort of fictitious thing we did. Then everything else here is basic algebra, and we end up with this conclusion that Q must be true. Okay. So we've tried to construct a world in which P is true. Okay. We end up showing that in this world Q must be true. So what does that mean? That means a world with P true and Q false is not possible. Now that is very interesting. So if a world with P true and Q false is not possible, it means that there's no world in which this implication can be false, because this row is not possible in any world. Because in any world where this row is possible, P must be true, but then Q must be true also, cannot be false. And so that proves that that implication is true, by proving that the false row cannot happen. End of proof. So now let me summarize what actually went on here. If you look at what effectively went on here, I sort of, by jumping into this world where P is true, I assumed P is true. And then I did blah, 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 and then I came out and showed that Q must be true. Showed Q must be So that's effectively what happened. So I could have said, assume P is true and show Q is true, but I didn't want to use this language like, assume P is true. Sort of, you'll get suspicious. I'm assuming something. Am I allowed to assume things? No, you're not allowed to assume things. And we're not assuming anything here. It's just effectively the same mechanics. Okay? What I did was I said, let me try and construct a world in which this row occurs, where P is true and Q is false. So, in such a world, let's see what happens. Okay? In such a world, P is definitely true. Okay? And in this world, you end up with an inescapable, undeniable conclusion that Q must be true. So the world in which true-false occurs is not possible. Okay. This type of proof of the implication is what we call a direct proof. And now you might wonder, well, it's kind of like, we just use the truth table. Why do we need to give it this name, direct? Well, we don't. Okay. It's just convenient to have a name for such a proof which is going to occur and recur and recur and recur, because, then when you're talking to the mathematics world, you will say, I am going to prove this using a direct proof, and everybody knows that what you're about to do is jump into a world where P is true, and then logically derive the fact that Q must be true. In fact, in the expert professional world, at step 4 is where the proof ends, because you don't need to then make the obvious conclusion that, this world with P true and Q false cannot occur. We don't need to take that extra step. All the mathematicians know that you're trying to show that this row in the truth table cannot occur. Okay? Now, I showed you this proof. It's summarized as a proof template in the text. So, if you want a proof template, look at the text. Okay, let's do another example. Okay. So, we're going to prove this implication. And, the idea is exactly the same. Okay. We fundamentally look at this truth table, look at this row, and show that this row cannot occur. Okay. So, even though I'm going to claim that I'm doing a different proof technique, and you'll see in books that it's a different proof technique, it is the same proof technique based on this truth table and based on the fact that what we're going to try to do is show that this row cannot occur. Okay. And you might have guessed that there must be some other proof technique if we're giving this a proof technique. So there's not just one way to prove an implication. I'm going to show you another way, but it's the same high-level idea, just a slightly different approach, different perspective, different mechanics. So, I want to enter this world, okay, where I'm trying to show that, if I'm trying to show that this row cannot occur. So let me see what happens if I'm trying to construct this row. Okay, so I'm going to enter a world and I'm going to look at it from a different perspective. Here I assume that P is true. Let me consider the situation where Q is false. It's the same type of world I'm trying to analyze. A world in which this row is occurring. So in this world where this row occurs, Q is false. So let's see what happens if Q is false. So step 1. Let's see what happens if Q is false. So I'm entering this fictitious world where Q is false. What does that mean? So we look at what Q is. Okay. So what does that mean? Okay, it means that, since Q is false, N is not even. So if N is not even, it means that N is odd. And we know from our previous discussion of odd and even numbers, this means that N is equal to 2k plus 1, where k is an integer. Okay, so that's what it means. That's what it means if I'm trying to construct a world, and in this world, I'm imagining, I'm pretending that Q is false. It means that N is odd. It means that N is 2k plus 1. So what does that say about P? What does that say about P? So let's see, what's P talking about? P is a claim about N squared, so let's just compute N squared. So N squared is equal to 2k plus 1 squared is equal to 4k squared plus 4k plus 1. Okay, so we've computed N squared, and we see that P is making a claim of the evenness. It's a claim about the evenness of N squared. So I should try to factorize this, as a product of 2 times something. So this part is divisible by 2. So this is equal to twice k squared plus twice 2k squared plus 2k plus 1. 1. So it's twice something plus 1. But that means that this thing is odd, because it's twice something plus 1. So this is odd. So n squared is odd. And so in this world, in this pretend world, I'm trying to construct a world, and I've constructed this pretend world where q is false, because q is false here. In this pretend world where q is false, it is not possible for n squared to be even, i.e. n squared must be odd, i.e. p must be false. N squared is odd, so p is false. What is the conclusion? A world in which q is false and p is true is not possible. A world with q is false and p equals true is not possible. And if this world with q false and p true is not possible, it means that the implication being false is not possible. And so therefore the implication is true, proved. Now this fifth step, we typically don't write it in the proof, because mathematicians is obvious. Again, you will observe that the high-level idea, emphasizing the high-level idea, is the same. It's based on this truth table, showing that this row cannot occur, but the mechanics are slightly different. In this situation, you start with the world in which p is true, and you show that q is true. In this situation, you assume q is false and show p is false. Okay. So that's the difference in the mechanics. Okay. Here you assume p true, show q true. Here you assume q false, show p false. This method of proof is called a proof by contraposition, or a proof of the contrapositive. And, okay, that's the name of the proof, the technique. But the idea, the high-level idea of both these proof techniques is the same. The advantage of knowing the name is if you see somewhere, I'm going to prove it by proving the contraposition, or a proof by contraposition, you know this is what's going to happen. You're going to enter a world with q false and show that in this world, p must be false. Okay? Now, I want to emphasize again, they're the same proof technique based on this row of the truth table. So you're sitting in the exam and you have to prove an implication. What do I use to do? Am I going to assume that p is true and show q is false? Am I going to assume that q is false and show that p is true? How do I do it? What's the mechanics? I forgot. What is it? No. Okay. Don't panic like that. Go back to the truth table. Okay? And that's the fundamental reasoning behind proving an implication. When you look at this truth table, you will see that, okay, I have to show that this row cannot occur. Two ways to show it. Pretend like I'm in a world with p true and show that this cannot happen, so I must show that q is true. Pretend like a alternative approach. Pretend like I'm in a world where q is false and show that this cannot happen, so I must show that p must be false. Direct and contraposition proofs. Okay. There are other ways to prove implication. You can pretend you're in a world where p is true and q is false. So try to construct a world where this row occurs. Okay, and if you do derivations and show that all kinds of nonsense breaks out, then that such a world is impossible. That's a proof by contradiction of this implication. We won't get into that at the moment. We haven't even talked about contradiction yet. So there are, other even more powerful ways. Okay, so practice. The speedy race. Woo, 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 woo. All right. Look at that. Okay, practice. So prove. If 4 to the x minus 1 is divisible by 3, then 4 to the x plus 1 minus 1 is divisible by 3. Okay? Yes. P, here's Q. So it's slightly harder than either of the ones I did, but that's why it's practice. and do the practice. Now, if you're having difficulty, this is covered in the text. Okay, but let me just illustrate this implication in action. So let's consider the example. Let's consider a world in which x equals 2. Okay. So let's look at what's p. So what does p talk about? P talks about 4 to the x minus 1. So 4 to the x minus 1 is 4 squared minus 1, which is 16 minus 1, which is 15. And that's divisible by 3. Okay, so p is true. Okay. Now, if this implication is true, remember, we argued that if the left side of an implication, of a true implication, if you know that the left side is true, then the right side must be true. Okay? If the implication is true. If the left is true, the right must be true. So let's look at Q. So Q is making a statement about 4 to the x plus 1. So that's 4 to the x plus 1 minus 1, which is 4 cubed minus 1, which is 64 minus 1, which is 63. And look, 63 is divisible by 3. In fact, 3 goes into 63 21 times. Okay. So divisible by 3. So Q is true as expected. That's that implication in action. But now you're asked to prove the implication. So you have to prove it. You have to prove that this row cannot occur for any choice of x. That if this side is true, then that side is true. Now at the end, are you going to know whether this side is true? No. Okay. Reasoning in the absence of facts. Are you going to know what x is? No. Okay. And that's what's subtle about proving such implications. Okay. You have to sort of approach it in this general way where the goal is to show that this row cannot occur, and then you pretend that, for example, if you're using a direct proof, pretend that you're in this world. So that means that P is true. What does that mean? What does that say about Q? And does it imply that Q, does it show that Q is true? Okay. So that's practice. Okay. Let me now consider disproving an implication. Disproving implication. Okay. So let's consider the following implication. If x squared is bigger than y squared, then x is bigger than y. So x squared and x and y are integers. So x squared greater than y squared implies x is bigger than y. So I claim that this is not a true implication. And for it to be a true implication, it must be the case that this row can never happen no matter how you choose x and y. If you find a single world, a single situation where this row occurs, the implication is not true in general. Okay? So let's see. Consider x equals minus 8, y equals 2. So this is P, this is Q, and we have P implies Q. So let's look at P. So P is talking about x squared versus y squared. So x squared is 64, question mark. And y squared is 4. And is it greater than? Yes. So P is true. Okay. Now let's look at Q. Q is talking about x versus y. So minus 8 greater than, question mark, 2. And that's clearly false. No. Minus 8 is less than 2. So Q is false. I've managed to find a world. I've managed to find a situation where this row has occurred. P is true, Q is false. That means that the implication for that world is false, and if it's false for any world that we can construct, then it's false in general. Okay. So this implication is false. And you can think of such implications written in this way as saying for any x and y. So they're implicitly quantified. Okay. So it's false, and the way we showed it's false is to find a single world in which it is false. This is called a counterexample. A single counterexample suffices to show that an implication is false.